Petri was Petri is
Yes. Yes.
still on in concept.
Yes.
Okay, so this is Chris Williams from UC Riverside University in California. He's a PhD student under the supervision of John Baez, and he'll basically tell us how interconnectedness is done in his research group using category theory with a different approach from the one we just saw.
All right, thank you. Hi. So yes, my name is Christian, and I just began my doctoral studies at Riverside with Dr. Baez, and I am really excited about this this event and this project for a lot of reasons. And so something that's come up in a lot of the conversations even before this event really started was the important difference between openness and being closed. The huge difference in society and in conceptual systems between an open system and a closed system. And it's a really important distinction. It is what decentralization and these kind of ideas are all about, and why they're going to benefit us so much. And so hopefully this is more of a leisurely detour with the category, the basic way that category theory would formalize just kind of a one-dimensional open system. And the way I'm seeing it so far is that the Petri nets are really going to be the workhorses of this whole thing, but then the category theory is kind of the underlying DAO, or the universal substance that's going to be more flexible and fluid and is going to help communicate between all of it. And so, so hopefully that will make it a little simpler. So at first it's going to be just a review of kind of the basics of category theory. So it's going to be looking at the stuff that we've already been talking about. So Pavel was talking about, they are open Petri nets, and he was talking about the boundaries. And this is just the exact same thing, looking at it from the outside and how you would formalize that categorically. And we were talking about the string diagrams, and this is going to incorporate that, and it's going to be one version of a simple formalization of that. So, so first of all, okay, so I'm just going to give kind of the basic general idea first, and then we'll break it down and explore it. So I'm going to be talking about a thesis by one of John Baez's students, Brendan Fong. It's called The Algebra of Open and Interconnected Systems. And it is mostly centered, so it is, I'm going to go against the grain of the talk. Y'all use the word spans. I'm talking about the exact opposite. It's a cospan. But it's just the idea where you have basically some kind of central structure, and then you have these legs of a cospan that pick out inputs and outputs. So in general, these, we could have these just be finite sets. And then we're going to take this set of species or places, the discrete elements of the Petri net or whatever structure we want to explore. We give it a functor that's going to apply more structure. So in the formalism that Fong shows, we actually just send a given set of places to the set of all possible structures that we could put on it. I don't know if that will be appropriate for this application or not, but in the theory, it was sufficiently general, and whether or not that's the most efficient in this case, I'm not sure. But you would send a given finite set interpreted as places, and then you just send it to the set of all Petri net. So you have it be the underlying set of places. So you have some S, and you're just equipping it with transitions. And so obviously the functor is doing all the hard part, but you're kind of separating between the aspect of being an open system and then applying the structure. That might be a good thing. I'm not sure. So, so this is the basic idea. You just have these sets X and Y that just serve to point out the inputs and outputs of your system. So when they point here, they're carried along the functor, and they're essentially pointing out the inputs and outputs. And so this is essentially the same concept as the nets with boundaries that we were just discussing. And we're going to see how you formalize composition of these cospans in the way that they just pop together the things, the congruent boundaries that should fit together. So let's back up some. Okay, so a cospan is just a diagram in a category of two morphisms that share a codomain. So you call the top the apex, and these guys the legs, and these guys the feet, and they are serving to provide this openness and just pointing out input and output ports. So it's a pretty simple idea. The only question is, so we want to compose these laterally and connect. If these are the, yeah, I need to draw an example. It's not a lot of room. So let's say we had, this is X, Y, and some Z, and Y is serving as the output of the first system and the input of the next. Then of course we want to stick them together and compose. You get the idea. So we just want to pop those together and identify them via the relation that they are being pointed to by Y. So this is formalized with the notion of a push-out. So let's back it up and slow it down a little bit more, just so that we can refresh on some of the basics of category theory, because it's actually very therapeutic and nice, and it's yeah. So I honestly like explaining it to friends and stuff, because it's just a simple beginning. Anyone can see how you can begin to formulate these simple ideas universally, rather than defining a product 1,000 times in 1,000 different mathematical subjects. You say it purely in exactly the essence of what it means. So an example, we can start with the product, even though it's not going to be relevant here. But basically, given some diagram, there's two ways to encapsulate all of its information. And they're called limit and colimit. And so if the diagram is just two distinct objects, the limit is called a product. And this is characterized by being the unique object such that given anything else mapping into this diagram, there's going to be a unique factorization through the product such that these diagrams commute, which means this path is equal to that path, and that path is equal to that path. And so this is motivated by the original example of just products of sets. So we take the Cartesian product, it's preserving all of this information. So if we had any two functions in there, we could take the product of functions and then take the corresponding projections, and everything would work out great. It knows everything about this diagram and nothing else. So the way you take a product of functions is you would send C to f of C, g of C. So preserving all the information. So the opposite here would be the coproduct. And in the case of sets, it would be the disjoint union. You include them in, you glob them together, and then given any other mapping out of the diagram, you have the similar globbing of functions that's going to preserve everything involved. So that's what we're going to be doing here. So instead of just having two distinct objects, you consider, well, it's kind of interesting. So we're going to be talking about cospans. So when I was saying before we had the legs and the feet, the span is the opposite, where it's one guy looking down at two guys. So you could say the head, the arms, and the, I don't know. It's not an exact. So we're doing a similar thing, and now we're pushing out here. So we have two cospans that share the central object. And one side it is the output, and on the other side it is the input. And you see how both of these are cospans, but actually at the central object it makes a span. So it's kind of a little simple dualization happening. And so we're talking about the push out here is what's going to do just the popping together of the nodes. So so just to see how this works in the case of sets, the push out is, let's say we had A, B, and C, and this is the diagram now that we want to summarize. Then the push out is the unique, so it's kind of a generalization of a coproduct, so that's why you use that notation. And so it is basically a subset of just globbing B and C together, except you identify, you quotient out by the relation whenever F
You should
is...
really say subset.
What did I say? Did I say something else?
It's a column, it's not a subset.
But now he's talking.
This is a subset of the product. I mean, it's the coproduct. Yeah. So first we disjoint union B and C together, and then we're quotienting out by the relation where whenever f of A equals g of A, which will be right here. So just whenever the output is the same as the input on the other side, that's what pops them together.
So it's like merging the places in S and S1, identifying the things that are hit by the same elements of Y.
Mm-hmm.
Okay.
Yeah. So think back to that first diagram, or the Y here pointing to both things. It's just going to pop them together. So yeah. So here, in the case of sets, it is BC such that f of A equals B and G of A equals C. So that's pretty much all there is to it. And the idea is now that we have an idea of composing spans, we can now, whenever a category has finite colimits, so for any product or all of those downward limits that we were talking about, product and push out.
I don't want to but I don't understand that formula at all.
This one?
Yeah, it's not a pair of elements.
Oh, sorry about that.
That's what I mean. It's not subsets. It's not limities. It's a quotient.
Yeah, sorry about that.
Of a disjoint union.
Yes. So I'm forgetting how to write it.
You find an equivalence relation on the disjoint.
Yeah. So write B plus C and then write diagonal line quotient.
Yeah.
Get
just
to the brackets.
Yeah. I forget how you would write it in the constructive notation, but just where the relation B is congruent to, or B is
If there exists an A such that.
yeah, there exists. Yeah. Sorry about that.
And this makes sense. You have some nodes in this system, some nodes in this system. You just put them next to each other, but then identify.
The things that are hit by the same element of Y, yes.
But the problem is, it's a quotient, it's not a subset.
Yeah, actually you can avoid the curly brace on the left and put it after the slash, because B plus C is already the... No, wait. Yeah, just like write the slash, curly brace.
Yeah.
Curly brace there. And then delete the curly brace in the string. No, that's perfect. No. Yeah, that one, exactly, perfect. Yeah, okay, good. This is good, yeah.
Yeah. That's just kind of a weird way. I think there's a simpler constructive set thing.
Yeah, no, it's just like sheet notation, but when you work in set, that's unavoidable.
Yeah.
Notation.
Huh?
Who cares about notation?
Exactly.
Yeah.
We don't want
We all get,
Notation is the co-limit.
We are computers, we're humans.
yeah, we all get the idea. So, so this is what allows us to compose spans, or cospans. And so once a given category has all finite colimits, then we can create a category from it. So let's say C has all finite colimits. Then you can create a category called cospan of C, where the objects are objects of C, morphisms are the cospans, composition is push out, and there's a, so now we have to do a quick review of the monoidal category stuff. Yep.
Since push-outs are associative only up to isomorphism,
Yeah.
basically there are, I suppose, two ways to do it. The first way is considering isomorphism classes of push-outs.
Yes.
And the second one is considered a full-grown, like, two-category or bi-category.
Yes, we're using the first approach for this case,
Okay.
but yeah. In general, the two categorical.
There is a third
probably
approach,
better.
which is my favourite way, which is just pretend there isn't a problem.
Yeah, I mean, in the end, it turns out to be
It always ends up
These are
mattering.
bureaucratic issues, right? It's always just bureaucracy.
Yeah, but when you
So-
work with two categories, actually you have a lot of stuff to say. So I suppose Brandon is studying this now.
Yeah.
But yeah, okay. It was just like to clarify which approach we.
Yeah. So yes, isomorphism classes, cospans. All right. So quick review of the monoidal stuff. Although I know we've already talked about it. But since we're trying to unite the normal categorical view with the string view, so it is just a category that's equipped with the notion of tensor, that is a functor from the product of itself to itself. So you can tensor objects, but a functor also tensors arrows, and these can be thought of the parallel process pattern. So you have B, C, T, and their tensor, like we talked about, is the arrow that represents their simultaneous occurrence. So, so the idea is that when C has finite colimits, or even just finite coproducts, we can use the coproduct as the monoidal structure. So this is actually very different from products. So we were talking about whether or not we can duplicate information and stuff with classical computation. We're going to see that this this thing about open systems is just a because it's not Cartesian. When we're used to just having like sets of memory and manipulating that, it's a totally different approach to computation. And you know, I don't know much about that, but I know that that's true. So we're going to see that this is.
That's classical logic for you.
Yeah. So we're going to see that this is actually a really nice category. It's better than a monoidal category. It's actually something called a hypergraph category, which is compact close. it's compact close plus the notion of being able to merge and converge wires. So we get the idea of a monodal category, and then symmetric is just adding the symmetry of objects. So, well, yeah, I don't want to get too much into the stuff about monodal categories, but so you have this braiding, and for the case of a symmetric monodal category, it is an isomorphism, which is definitely what we want. It seems like we want them to be equal, but we don't. But we do want them to be isomorphic. So, sorry, hold on a second. Okay. So we get the monoidal structure of this cospan category from taking coproducts. So we have given some identity cospan to itself. So these are just identity of C. By the notion of a coproduct, the universal property of a coproduct is that even though this is just pointing to itself, there's still this unique factorization through the coproduct with itself. And this is called the co-pairing, which can generalize to any F and G. And then we have the monoidal unit in this case, because the monoidal structure is coproduct, is just the initial object, or since we're usually just going to be talking about finite sets, it's just the empty set. So this bang, or whatever it's called, the initial object, every object has a unique morphism from it, from the initial to it. This and the co-pairing is what gives us the structure that we need. So let me okay, so in general, we're seeing that with these open systems, the monoidal structure is really easy. We're usually just juxtaposing two systems, and we really don't have to do anything else. And the same thing is true in this case. So,
so the coproduct of two cospans is just substituting like the coproducts of the objects and the co-pairs of the arrows?
Yes. So given to given two spans, their coproduct is just taking the coproduct of the.
Okay.
Yep.
And those are the co-pair arrows of the arrows on top.
Mm-hmm. And this effectively just takes two of these Petri net diagrams and just puts them together, because we're just doing disjoint union. That makes sense. Okay, so let's skip ahead to the interesting part. So this is better than just a symmetric monoidal category. It's a hypergraph category. So the way Fong describes it, just as symmetric monoidal categories equip monoidal categories with just enough structure to model crossing of strings. So the switching of BA to AB is just crossing the strings. Hypergraph categories equip symmetric monoidal categories with just enough structure to model multi-input, multi-output category interconnections of strings of the same type. So, so the idea is that a hypergraph category is where every object also comes with a bunch of really nice extra structure called a Frobenius monoid or Frobenius algebra. And these things are really interesting and have a ton of connections to theoretical physics and stuff, and they're really nice, and even just like fundamental logic and stuff. So hypergraph category, it's a symmetric monoidal category, plus every object is equipped with a Frobenius, special commutative Frobenius monoid. So this is what keeps track of all of the structure that can happen when you have a ton of inputs and outputs, and you can switch them around and spin them. So Frobenius monoid. So that structure is a unit, a multiplication, and co-unit and co-multiplication. And it's not a coincidence that these use the kind of symbols that you see in adjunctions and monads and comonads, because one of Baez's students actually proved that every Frobenius algebra is induced by a ambidextrous adjunction where it's like both a left and a right adjoint, and somehow that has a ton of really important connections with physics, because a topological quantum field theory is somehow determined by one of these Frobenius algebras or something. So I'm really interested to explore how much of that seemingly a lot fancier stuff will be incorporated into this, because it's not going to be irrelevant, even though it is fancy. So, co-multiplication. So, y'all came to see strings. I need to hurry up and show you some strings. So, okay, so we have a multiplication from the tensor to itself. So back when I was talking about the co-pairing, this is how we're going to do that. And take two instances of the object and you're merging them. And the unit is from the monoidal unit, which in this case would be the empty set, to x, and this is starting an object. And then, I don't know why I'm writing so big, and the opposite is co-multiplication, is splitting it up. And the obvious diagram. And the co-unit is kind of ending some object, x2, 1. And so the idea is that a Frobenius monoid is really nice. It's a misnomer because it's simultaneously a monoid and a comonoid, and they're compatible in a nice way. So, for example, so we know a monoid is associative, like we were talking about, and then the way that you express that is you multiply the first pair first, and then the second pair is the same as multiplying that and then that. Associativity, and then co-associativity is, of course, the opposite. And then the unitality is the fact that if you are just multiplying by the unit, it's going to be the same as the original object. And co-unitality is the opposite. And so, commutativity is the other important part. So it's also working nice with the symmetric monoidal structure. So that you can twist and it is the same as just multiplying, and vice versa for the co-multiplication.
And specialities. You have to see the three.
Yeah. Yeah, so then the last two are called the Frobenius and the special, and they're describing the fact that the Frobenius is that that the monoid and comonoid work together. So, like the similar to the diagram that Jules was talking about, is the same thing as the tensor of a co-multiplication and a multiplication via a it is equal to their sequential composition, and to the opposite one where those are switched. And the special is, like Fabrizio was saying, that immediately the co-multiplication followed by the multiplication is the same as doing that. So these are all the nice things that you get from this structure. It's allowing you to intertwine the strings however you need. And
it actually is one more thing in our hypergraph category. That is that when you have two Frobenius structures on two different objects, when you tensor the objects together, the Frobenius structure of the tensor is the tensor of the Frobenius structures.
Yeah.
And so basically you have the additional property that, because this thing is defined just on one object, but basically hypergraph means that this thing is also well behaved with respect to compositions of objects. But anyway, yes.
Yeah. And then we see that from all this, you get the fact that they're self-dual compact closed, which is the nicer thing that normal computation doesn't have. And it's one of the examples of the important difference between open and closed systems. So, given some, so the composition of a unit and a co-multiplication is what we normally think of as the there's kind of two notions of unit, and this is the one that we were talking about that's going to swap functions around to their dual. This is how you formulate that, and then you have the opposite. And so given some f x to y, although, I mean, in string diagram it would just be like that, you can pre and post compose with these to flip it around. So you get the so-called name of the morphism, and yeah, it has to do with the way that you can dualize a function into its evaluation and co-evaluation.
And one thing is that obviously, like those caps and caps on the right, there are the things that Jules showed that for which the Yankee equation solved. The thing is that if you compose those things on the right into a snake with these supplementary things with the Frobenius axioms, you can show that they reduce to the identities.
Yeah.
So this is why that's a legit.
Yeah.
So actually, the Frobenius axiom generalizes to putting it on string.
Exactly.
Yeah.
Yes.
And so we prove, they proved coherence stuff about why we can still do all this and everything still works in the monoidal sense. And McLean's original proof of coherence of symmetric monoidal categories just carries over, because basically hypergraph categories are just like,
It's the jolly boy.
you know, a bunch of tensors, or like, it's only adding this multi-input, multi-output thing, and everything works coordinate-wise. So everything works out. And so adding on to that list of a given category with finite colimits, you create the cospan category. We had the objects were C morphisms, iso classes of cospans. Composition was push out. monoidal product. Sorry, I didn't really cover that one well. So,
Co-product.
yeah, it's just the original co-product. Well, it's going to be the co-pairing of those. So when we had, when we were talking about x plus x, factoring through the identity, this is how we get the multiplication.
Or the Frobenius thingy, yes.
Yes. So the hypergraph maps are just from the universality of the coproduct and the initial object, and then the coherence is just inherited from C. We don't care about that. Hypergraph is all that nice stuff. So like the unit is the co-pairing. The multiplication, co-multiplication is just the opposite arrow because we have the ability to take opposite arrows in this. And then, the bang and the opposite bang. So this is really nice. And so the idea is, beyond this, all we have to do is add a functor that's applying more structure, and then just ensure that we're preserving that structure. So it's just called decorating a cospan, where you're taking the apex and sending it to, the set of all Petri net structures that you could put on that set of species or places, and then we just impose the extra structure that, to consider morphisms between these structured cospans, you have to preserve that. So we have some input-output, and we're applying a functor to some f of s, which is the set of all Petri net structures that you can put on it. And the idea is that the monoidal unit and set is just picking out one of those. So this is just the one element set. So it's picking out the Petri net that we want. And then given two decorated cospans representing two different open Petri nets, a morphism between them is not just a normal morphism of cospans where these commute, but it also has to, map our Petri net structure to the other one. And once you have that, it does pretty much everything you would want in the basic theory of all these, of a categorical view of these open Petri nets. Like I said, I don't know if it's going to be the right thing that we need, but it introduces a lot of concepts that I think will be essential to.
So, in that example, you have basically a representable functor that you're going to set, and you are considering sets of Petri nets. Is there a way to, does it work if instead of a representable functor in set, you have an enriched environment? So basically you want to go from S to the category of Petri nets directly and require that a morphism of cospans becomes a morphism of Petri nets.
Yes. Yes. I think we might end up doing that. That was kind of the thing that I wasn't supposed to talk about because it's not published yet. But it's not going to be long until it's published, and it's not a big deal.
I understand that it's technically challenging because, speaking of limits and co-limits in an enriched environment is one of the most obnoxious things.
Yeah,
ever.
I don't think we'll have to deal with the actual enriched case very much.
They still have to deal with Max Kelly's papers.
Yeah. So that's the basic idea. There's
Some limits are cool.
You like limits in a rich category?
Actually,
You're a masochist there.
No, they're just cylinders.
You have all this paper by Robert algebraic weighted co-limits using double categories.
Yeah, obviously you have to use weighted stuff.
Yeah, have you seen it?
Filter
I
stuff.
tried to invite out of it.
double categories are really cool.
Yeah.
That's the main idea. There is one other thing that was in the thesis about correlations, where if you impose, so a span can be seen as a generalization of a relation, and I don't want to get too into it. I don't know it well enough, but the idea is that you dualize this, and there's a notion of correlation, where it is basically an equivalence relation of the disjoint union of two sets.
It's a partition, basically.
Yeah, yeah. And the point is that when we're composing Petri nets, or his example was electrical circuits, there might end up being stuff that becomes lost and is redundant. And if you're retaining that information every time, you're going to be wasting a lot of energy. So, such a terrible drawing. But the point is, every time that you would lose information in the composition, there's an easy way to just modify the theory a little bit and only consider certain cospans that aren't going to be bogged down by that. So that might end up being relevant.
So I'm not sure, maybe you just answered the question I was going to ask you.
Yeah.
So I'll ask it now in case you have. So if I understand your construction, so you've got these open structures and their interfaces, and the sequential composition, you're going to take the outputs of one and the inputs of the other and do them together. And so the overall new space is the original space that places from the first, space that places from the second, plus one copy of that interface. But in some situations, don't you want to have no copies of that interface? Because it's sort of just sort of smoothly, the wires just go straight through somehow.
Sorry, what are the copies? And what are the copies of the interface?
So, so your construction for sequential composition, take two cospans, and the apex of the composite object is the disjoint union of the two apexes, quotiented, so you only get one copy of these bits of the interface. But I can imagine a situation where the answer you want is the apex, which basic places or whatever, does not contain even one copy of the interface, because the interface is only there to sort of glue interaction. Once you have that interaction, it's sort of like hidden somehow in my understanding.
Yeah.
Doesn't this amount to do a push out of an identity cospan by another thing? And in this case, you have a push out with two identities in the square, and the apex stays the same.
Well,
so the one question is, does that situation arise, and so how do you deal with it mathematically? I'm not sure about the first one. The second one, it can't be a quotient because you'll still keep a copy. You can't quotient and get rid of a copy. I thought some kind of equalizer, remove things.
well, the quotient would be essentially identifying things. And so at that point, on a computational level, we could just throw the information out or something. At that point, it's no longer in the theory. It no longer matters to the theory, so we could.
You don't even have the interface at this point. Like, this is a syntactic thing that keeps tracks of inputs and outputs, but until you project this with a functor in some library of components, those are just places. So for instance, if all the wires go through smoothly, then you have an identity cospan, and when you push out, it just disappears because it's an identity. While if you have the situation in which inputs go here and outputs go here, when you compose with another span, you will keep track of this, but then in the end, when you go to correlations, this thing will fuck off because it's not connected to anything and will fall apart.
Okay.
And this is the only thing that stays in place. So yeah,
That is the same thing as in Pavel's situation, where you have like half a transition on the right, half a transition on the left, and there's nothing in the middle saying these things are identified. You actually identify, so you get one transition. The interface is gone.
Yeah.
So I had a question for you guys. Would there be any benefits to this decoration idea, where instead of just having a functor to PetriNet, we had the set of all the PetriNet structures that we could put on that finite set of places? Would there be any benefit to that, or would we want to just be working in the category of PetriNet?
Like, the reason why I think this is very interesting is that since you're keeping track only of inputs and outputs, you can basically change your component library as you wish. Like,
Yeah.
if you base your software on this kind of stuff, and for instance, in the future, we have some nice idea, we found out that Petri nets are not the best thing ever to do this stuff,
Yep.
you can basically just switch your component library, and you're still back in the game.
And if you can have some sort of ordering on your Petri nets, and say this one is less, it's like more fine-grained than the other one, then it would be very useful, because then you get this idea of a protocol, and by filling it in with a more fine-grained thing, that's like a particular process. But the protocol is just saying, like, as long as you follow these steps, then we're happy. And if you need some steps in between, that's fine. If you're
But to do that, you have to drop the isomorphism classes of co-spans, and you have to go full to categorical, and basically consider morphisms of co-spans. There are two morphisms in this case, that are basically just arrows between the apexes so that everything commutes.
So
But then you need two categories.
I think that we definitely will need
Yes.
to be considering net morphisms at the same time as I mean, we'll definitely need that, and so that's why I'm saying, like, I don't think this is going to be right.
But then, if you collapse these two correlations, you get that the home structure of every of these morphisms is opposite, and so you will naturally have an ordering when you of Petri nets when you go on the set side. And that's Carboni-Walters nightmare, basically, more or less, like, yeah, horrible stuff.
So rather than this thing, the way that I'm picturing it is, and I just have to talk to Bias first that it's going to be okay, but I know it will be. But we're actually in Petri, and we consider so yeah, rather than working through these sets, we're doing the same thing really directly, and we also have the two categorical interpretation. So, but yeah, the same ideas hold, they're just being expanded. There will be the corresponding notion of like a hypergraph 2 category and all that nice stuff. So yeah, basically.
I have an important question that has no answer.
Okay.
At least no answer yet. So open games are open systems. They're very strongly motivated by thinking about open systems theory. They don't fit into this framework at all. Essentially trivially, because they don't form compactized categories, so they can't. So
yeah, so how does the
question
openness work?
And I think that's a feature, not a bug.
So I think a partial answer to yours is the following. So if you look at open games, some of the structure is kind of general structure you see in lots of places. Some ports and some publishers and whatever. That sort of stuff ought to be amenable to general constructions. But the equilibrium predicate, which we'll see again, is really kind of way out there. And it's not surprising that stuff doesn't fit into many of these constructions because it's much more sophisticated.
Brendan implicitly makes very strong assumptions about input-output symmetry, interchangeability, which doesn't hold in general. So all these systems are time reversible, whereas open games are not time reversible, and in general you care about non-time reversible systems.
Yeah, so I think that generalization, that interaction will be really interesting. And but there's definitely going to be.
So I'm essentially saying this as a claim to as a challenge to anyone saying they have a general theory of open systems.
Oh yeah.
You're not saying that we have to discuss 4 hours about causality in open games and Petri nets.
Yeah,
I'm up for it.
Yeah, but
I mean,
counting in.
Yeah.
I mean, from an economic point of view, this equilibrium stuff came in from the forward-lookingness we have. And this is the general feature of social systems because they carry around a model of the system inside themselves.
Yeah.
You can go infinitely deep. And we want to go infinitely deep into that, and we have that in economics, namely Hazami time spaces, so which is a belief formation about the beliefs of beliefs of beliefs, and so you have infinite mirrors down to the where then the curtains appear, carrying the world. So
yeah, but yeah, just I guess the one like idea, as far as I can tell, that this represents is that Petri nets are really nice and structured, and just so you all know, it hasn't been mentioned yet, but Petri nets from a categorical perspective are presentations of a free symmetric monoidal category. So a given transition is thought of as a morphism from the tensor of its inputs to the tensor of its outputs. It sounds pretty obvious, but just to remind y'all that explicitly a Petri net can directly be understood as a category and not just as an object in a category. And so that's important.
To add on to this, if you you can run a Petri net, and then if you want to fold something over the history of the Petri net, this is exactly the types of your functions that need to run over.
Yeah.
This is something very natural. This is where you want to interface with this logic programming.
Yeah. So anyway, the basic idea of this talk was like, there's going to be these local, very structured, nice, restricted symmetric monoidal categories, but then whatever the structure is out here, it's going to be a lot more fluid and general, and it's all, I think one of the big questions is going to be how to synchronize between those two structures. Yep.